Presentation for you today. Mike Davis is going to speak about nuclear power and the Navy, and we look forward to hearing from him. Other than that, I'll turn it over to you.
Thank you. Good morning. Thank you, John. Thank you, Senior Men's Club. Sorry that Mark, who invited me, couldn't be here today. I was in the Navy for almost 10 years, and I was a nuclear sailor and attached to a submarine. So like every thorough Navy presentation, I probably could bring this closer, huh? I'm going to tell you what I'm going to tell you, then I'm going to tell you, and then finally I'll tell you what I told you. Make sense? Don't worry. I say again, no one will be left behind. Just as I have it in the title, I'll talk about the U.S. Navy, nuclear power, submarines, and SMRs are small modular reactors, and that's a question mark. We'll mention it a little at the end. I may jump around a bit, but I will try to use my personal journey, my life story, as the kind of jumping off point. So feel free to ask me questions. I know there's a Q&A after, but any clarifying questions, if I'm not holding the microphone close enough to my mouth, say a little louder, or if I use an acronym, or if I say a concept that you're not familiar with, you know, I'm kind of a nerd. I'll share some technical nerdy things, but I want to keep it lighthearted and enjoy some laughs from start to finish. So, but I do tend to be very detail oriented, and if we go too deep, we can always come up for air, right? Submarines don't sink, they submerge because we expect them to come back up. All right? And we don't want any men overboard, right? We'll fish you out of the water.
Lights, action.
All right. So, like I said, welcome. If I was giving an address to sailors, one way I could start the talk would be for me to say greetings, and the whole group would bellow back the same. You want to give it a try? Greetings. Greetings. Awesome. I am a deep thinker, but I also get easily distracted by proverbial squirrels. So I've got a script to keep me on track, but also I don't want to go too off the beaten path and say anything classified. So here's our token slide on classification. And I got the script, so if I lose my way, I can find my way back. I'm a little like Linus from the Peanuts. This is my little security blanket, right? On a more serious note, what soldier would venture into new territory without a map? Sailors use charts for navigation, so I could say this is my chart. How about that? By the end, you'll know me with some depth, not as deep as submarines go, but we'll get close. Of course, I'm a typical 17-year federal employee and must follow procedure. I've been institutionalized. Anyone here been institutionalized? Does everyone know where the emergency exits are? What about the bathrooms? Where do we meet in the event of an evacuation? I'm not being serious, this is lighthearted humor, but this is like every presentation I've ever had in the Navy and in the shipyard. And then is everyone signed in so we can make sure everyone makes it to muster in the event of an evacuation, right? So you get me, right? We are all in. I'm gonna run this ship as if I was still on active duty or like when I was a civilian employed by the Navy. You may have noticed a clear lack of classification markings on the first slide, except that it looks like I'm adding classification markings here, but welcome to the Navy. If it's classified, it must say it's classified. If it's not classified, it must say it's not classified. So there's nothing classified in this presentation, just to be clear. And what is classification? Maybe some of you know, maybe some of you don't. We have confidential, secret, and top secret. Anyone here have an experience with that? A few of us? Okay, so it goes something like this. If it may cause damage to national security, it's confidential. Serious damage to national security, it's secret. And exceptionally grave damage to national security, it's top secret. And you may have heard the acronym TSSCI, top secret, sensitive compartmented information. In order to access any classified materials, you have to have a background check, and there are different kinds depending on the level of clearance you need and the type of information you'll be accessing. I had a single scope background investigation to become a nuclear sailor. And if you've ever heard the phrase read in, that is something you have to do in accessing sensitive information. So I am reading you into this presentation. But you also sign your life away, and after leaving the specific compartment you've been read into, you have to be read out or sign a non-disclosure agreement. Maybe some of you have had to do that. Only classified materials comes with serious consequences if you violate the non-disclosure. So no, I won't have to kill you if I tell you, because I'm not going to tell you anyways. But that's the nature of the job. I will say that a lot of people have a hard time with it, though. There are those people who want to know, right, classified materials. And you never know if you're talking to someone in intelligence or even counterintelligence. When I worked down in Charleston, South Carolina, I was told, hey, this is where all the spies are. And it's like, what? Not DC, not somewhere else? And like, nope, right here. We've got a command locally that people want to know about information. So if you're out at the bar or anything like that, don't blab your mouth, because, you know, you could be talking to someone from the US government, right? And so even in here, right? But I've been at a bar near a shipyard and listened to people talk about the work that they do right inside the shipyard. And so, you know, just for all you kids out there, ever hear the phrase, loose lips sink ships? So if you got a job to protect information, please do your job. So I've been on a submarine mission in the Pacific, forward deployed out of Guam. I have a little blow-up globe over there, so if you don't know where Guam is, it is way out there in the Pacific. Because I was an officer on the submarine, I had to be read into the top secret compartment. Just getting to the place was an ordeal, so the place where they read me in, which was an ordeal, which is a good thing. Think about a bank vault and what it would take to be escorted into one. That's sort of the idea. And then think about buying a car and the amount of paperwork you have to sign. Sort of similar. So we've got physical security and we've got legal security. I've never been arrested by a cop, but I've been in cuffs, so to speak. Beyond classified information, we also want to protect operations. Operational security is also known as OPSEC. We love acronyms. Where the submarine will be and at what time. So we don't talk about ships' movements for obvious security reasons. Our enemies would like to know where it's going to be, right? So we won't share it in emails or on Facebook or in tweets. Twitter, you know. We actually had a problem with this in the submarine community. Husbands and wives or significant others would start to put the ship's movements in code so the spouse could meet them at the next port. And anyone who's familiar with the old days of submarines knew you had a familygram and you had a certain number of words that you could send home, and you could only communicate 3 times. When I was out there, we had email, so I could email every day. But since then, they've had to clamp back down and only use familygrams. So they take security very importantly. But do we just stop with classification? No, you guessed it. If we don't classify it, we control it. We used to have for official use only, if you've ever seen that. And now the bane of every federal employee's existence is controlled unclassified information. It's essentially the same as the old FOUO, but almost sounds a little cool, but it changed the rules. So then, if it's not classified, if we don't lock it in a box and say you can't spread it around because of national security, then we put it in the next box over that says, well, you can't share this either, even though it's not classified. And if you notice, unclassified's in all caps. Today, if we email or text, we say, hey, stop yelling at me. And in the military, it's not yelling, it's just all caps. And on a completely different note, we don't yell at each other in the Navy, but we do all caps each other. Anyways, we've got acronyms. Sure, if you've worked in any industry, you know that each one has jargon. But military and government jargon is pretty notorious. Here's a phrase for you. Ask the COB to print out a new POD so you can see your new AOR. Some of you may think I was speaking French or something. So I said, ask the chief of the boat to print out a new plan of the day so you can see your new area of responsibility. Why didn't you just say that the first time? We have acronyms, and I'm going to say it. We have acronyms of acronyms. It sounds like a unicorn, and it is. I saw it one time, and I can't remember what the acronym was, so you'll have to trust me a little. It was related to the name of a military program, so I don't even know if I could share it anyways. But we can make one up so you could see what I mean. A lot of people around here should be familiar with the Department of Energy. That would be DOE. What if we kick-started a DOE initiative called More Power, Less Effort? So DOE initiative, More Power, Less Effort, or DIMPLE. So we've got to laugh because I'm convinced some people sneak in acronyms for fun. And much information can be conveyed through humor, and it won't even feel like I've told you anything important. But maybe tomorrow you'll chuckle at this bubblehead, another name for a submariner, that you listened to that couldn't stop with his wisecracks. But seriously, if I get rolling and use acronyms or words that I haven't defined, please raise your hand and I'll be happy to pull you back into the ship. But if your questions can wait till the Q&A time, that would be fine too. Before 2005, I was born in Southern California. But interestingly enough, it was at a naval hospital. My father is a retired Marine, Air Wing. He was an avionics electrician, and then a drill instructor. So the question is, was I treated like a recruit? Well, when my father was asked if he treated his children like recruits, he responded, no, I treat my recruits like my children. As a child, I accepted that at face value. But with the benefit of hindsight, I can say, yes, of course he treated his children like recruits, obviously. Not a complaint per se, but just to say that I was well prepared to join the Navy. So of course, I grew up as a military brat, or a child of a military member. And remember my father putting on his presenter's persona. And he was a Marine, and a Marine's Marine, so stand tall and proud. If you can't dazzle them with your brilliance, you've got to baffle them with your BS. You get the point. And I also learned that it is a valuable quality to develop at all levels of military and government service. How to take seemingly nothing and stretch it to cover anything. Sort of like this slide. It's just a timeline, but I can talk for a while about it. You think that may be why we have problems sometimes with our government? Hey, I'm not accusing, just showing you how I was trained. Anyways, I was honorably discharged from active duty on December 31st, 2014. And the reason why I was invited here today has to do with what happened in between 2005 and 2014. In 2019, I was honorably discharged from the Navy Reserves. After my time being an active duty sailor, I worked at a nuclear shipyard, and feel free to ask me about it in the Q&A if you'd like. I'm going to focus more on the in between those dates. So my younger brother had joined the Army. This is after 9/11, and I really didn't want to continue with college. There was conflict in Iraq, so I joined the Navy. When you make life-altering decisions, don't be young and dumb. Actually, it was one of the best and worst decisions I could have made. Personally, I needed the kick in the pants, right? But come on, did you have to kick so hard? Take your licks and learn, right? If I didn't need the kick in the butt, I probably would have chosen differently, so it all works out. I actually talked to the Air Force recruiter first, and that guy couldn't have been more blasé. I didn't realize it then, but it's because it's so nice in the Air Force. Any Air Force vets here? Couple? It's so nice in the Air Force that recruiting wasn't that hard in 2004. So I instead walked next door to the Navy recruiters. I can hear you snicker back there. And as soon as I opened the door, I could swear that they had the place at a suction. Because as I remember, I was pulled right into the office. Actually, I worked there for a few weeks after boot camp, and they were a good group of people. Come on in. Here, take this test. It's just the practice one, but it's a good indicator. Wow, you just about aced it. Do you want to be a nuke? I didn't even know what a nuke was. The recruiters didn't know either. But they got bonuses for recruiting them. And hey, here's some literature, read it. Oh, pretty pictures, cool colors. Actually, the flyers were pretty cool and informative. In that office, I used that information to map out my career. I'm going to enlist. I'm going to be a reactor operator, nuclear reactor operator. Then I'm going to become a Navy officer and serve on submarines. Now kids, just because it worked out that way for me doesn't mean you can bank on that happening for you. Plan for contingencies, please. It did work out for me though, but not without grief and a whole lot of elbow grease, and that means effort for some of you youngins. My A school, or trade school, was one of the hardest academic experiences of my life. The difference in the couple of semesters of college that I had in this school was so significant that this school felt more difficult than the notoriously more difficult school that came after, which is nuclear power school. After that school, I'd go on to the hands-on trainer at Nuclear Power Training Unit Charleston in South Carolina, which for me was an old Polaris sub known as the moored training ship 635, the former USS Sam Rayburn, in the dirty water of the Cooper River in South Carolina. So what they did, and I don't have a picture of it, is they cut out the missile compartment, fused the ship back together, and turned it into a training platform. And if you have any connection to Bettis Atomic Power Laboratory, or Bechtel, they were responsible for my nuclear power training curriculum. Fluor Marine Propulsion, LLC, currently works with BAPL and holds the contract at the moment. BAPL, Bettis Atomic Power Laboratory. We like to read our acronyms. So I learned all about the construction and operation of the S5W plant and the S3G3 core, with which the S5W plant was refueled. And I will tell you what that acronym means if you don't know it. S stands for submarines, so we're talking about the nuclear power plant inside the submarine. S5W, 5, stands for fifth generation, and W for Westinghouse. So Westinghouse was the group that put the power plant in that submarine. But we refueled the core with a General Electric core. So if you're Team Westinghouse, you might be a little soar at that. And if you're Team General Electric, you might say, ah, we got one. So S3G3, similar. S stands for submarine. 3 is the third generation core, and then G for General Electric. And this was the third iteration of that design. And to make sure that we're not doing anything classified, I borrowed some quotes from Wikipedia to talk about these core designs. So this is a little dry, but although the design of the entire S3G reactor plant, core, piping, pumps, etc., saw only limited use, a designed version of the reactor core, S3G3, or S3G Core 3, was later used for replacement cores for the Navy's 100 S5W reactor plants when refueled. Another unique feature of the S3G Core 3 was the use of Y-shaped control rods versus the standard cruciform control rods used in the S5W core. The core also used a rod configuration called skew divergent for ease of maintenance. So control rods are what we use to start up a nuclear reactor. They are also known as poison rods. They absorb neutrons. And different shapes are experimented with to see the different dynamics inside the core. And so this one had Y-shaped control rods. And skew divergent is in reference to the arrangement of how the rods go into the core. So an easy way to think about it is if you take a stack of pencils, and that would be your fuel rods, but also your control rods goes inside the fuel rods. And if you were to twist the whole thing and they were to spread out, that was a skew divergent that General Electric had come up with. It made maintenance a little easier and some other things, but also made things very complicated if you can imagine the geometry of this nothing parallel to each other. But it was really cool. Remember, there's nothing classified in this presentation. My one caveat, if I present something from an open source like Wikipedia, I cannot confirm or deny whether the information is classified. Most of what can be found on Wikipedia is not classified, but that affords no guarantees. That being said, I really love the Westinghouse power plants, like the A4W in our nuclear aircraft carriers. So A for aircraft carrier, 4, fourth generation, W for Westinghouse. And I really love that General Electric core. So either you love me because I love both sides, or you hate me because you root for one team or the other. It's all sorts of complicated. Simple design and complex operation. Those old cores, they were designed simply, but the operations were complex. So in reality, you want a complex design. So if we have any engineers, right, you put in that elbow grease, that effort, and simple operation. Remember, we have 18, 19, 20, 21, 22-year-olds operating these nuclear reactors. So simple operation is preferred. And don't forget, these operators are sleep deprived, hopped up on stimulants, mostly legal, I'm pretty sure. And if they're on submarines, they're also breathing a slightly lower oxygenated atmosphere because partial pressures. What are partial pressures? All right, so we have to take a moment to explain partial pressures on a submarine. So when you submerge a submarine, the pressure of the water increases. The actual submarine is designed to collapse in on itself. Some people experiment, put a string across and a washer in the middle and watch that washer go down as you go down under the water. There's a place on a submarine where one of the ladders is on a slider, and A-gangers, the non-nuclear mechanics, they use that as a depth gauge. I saw they put little Sharpie marks on where the ladder would slide to, and like, okay, 100 feet down, 200 feet down. So they had their informal depth gauge because the submarine collapses in on itself. But that also means the atmosphere is more pressurized. And since the increase of pressure will force more gases into your bloodstream, the Navy actually calculates how much less oxygen it needs to maintain in the atmosphere, the artificial atmosphere of the submarine, to keep you oxygenated to the right amount biologically. Since more oxygen is going into your bloodstream at the increased pressure, we can lower the percent of oxygen in our breathing air. Yay! Bring on the headaches. Actually, there's good logic to it. It reduces how fast fires can burn. and that's pretty important on a submarine, to not have fires, but if you do, have it have less oxygen. It also makes people more lethargic, and so they make less noise. And submarines are about clandestine operations, so making less noise is also a good thing. And it makes it easier to maintain oxygen at that lower threshold, because we got to manufacture our own oxygen. That being said, it doesn't make it fun. Breathing artificial atmosphere will age you visibly. But you can regain some of the elixir of youth when you return to natural atmospheres, but still. Getting back to operating this core, it was weird. You pull these rods, stop. Pull those rods, stop. And after a certain time in core life, we change the order. Now you pull those rods, stop, and you pull these rods. You get the point. It made my pattern recognizing brain light up, though. I loved it. Well, I hated having to learn it, but once I did, I loved it. And it kind of ruined me for learning S9G, S submarines, 9th generation General Electric cores. Oh, you pull the whole bank of rods until the reactor is critical. Yawn. Of course, that's the newer engineering, but what can I say? I love the challenge. So how old was I? I turned 21 in boot camp. 2 years later, I was training mostly 20-year-olds how to operate the thing. I had good grades, so I actually got a position as a junior trainer. Staff pickup was the old term. Junior staff instructor was the new term when I got the position. So I qualified as a Navy instructor and got to teach, not classroom style, but hands-on, more one-on-one practical training. Oh yeah, and we had an IDE, interactive display equipment, or simulator, for propulsion plant operations. While the simulator was good, it did not mimic the hours-long transients we experience in real nuclear reactor cores. The NRC website defines transient, and so this is what's happening inside the core, okay? A change in the reactor coolant system temperature, pressure, or both, attributed to a change in the reactor's power output. Transients can be caused by 1, adding or removing neutron poisons, 2, increasing or decreasing electrical load on the turbine generator, or 3, accident conditions. So when you operate a nuclear reactor, you are removing a rod that absorbs neutrons from the core. This allows the neutrons that are not absorbed, right, to interact with your nuclear fuel, leading to fission, or the splitting of atoms, which releases large amounts of energy and other elements on the periodic table, or the chart of nuclides if you really want to geek out. I have a book of chart of nuclides on the table. It's like the periodic table of the elements blown up. I probably shouldn't say blown up on a nuclear talk, but expanded out. Some of these elements actually affect the existing neutrons in the core, so the core is changing its power level on you, but in such a small, minute amounts that it shows up as an hours-long transient. And the simulator is not programmed to run those longer-term transients, only the shorter ones. So really, when I qualified on that core, I actually qualified on 2 different cores, the real one and the simulator. But I'd say that in jest, because it's more like you driving your car with a full load of people or just by yourself. It operates a little differently, but it's really the same car, if you know what I mean. The real fun with the simulator, though, is running reactor accident drills. They're the worst. One of my accident scenarios affords me seconds to respond to save the core from damage. And that makes everyone a bit uncomfortable to hear that, but I had some good teachers, and they told me that if you see that scenario happening, so I'm looking at my instrument cluster, pick up your coffee cup and take a sip before acting. Now, he's speaking metaphorically, not actually do that. People get pretty mad if you do that. But what he's trying to say is there's plenty of time. For example, can someone give me a 5-second countdown? Oh, can you do it out loud? Engineering officer watch, steam line rupture casualty, screaming the reactor. Did I get it? Did I twist my hand before you got to the 1? Okay. Now 5 seconds is not the number, but I don't want to say the number because I think that might be too much information. But you can see how, like, I simulated sipping coffee, which I would never really do. But there's plenty of time. So when you are a reactor operator and you're looking at your pressures and temperatures in front of your face and the reactor power on your different meters, if you're always monitoring this stuff, your flow rates through the pipes, you see what's happening and you know what's happening, really high level of confidence, and you can act pretty quickly. Just calm yourself for a second. Yep, that's what I'm seeing. And you make the announcement and you take your action. You don't even have to wait for permission to save the core. All right, nuclear reactor, inside and outside the Pop-Tart. So we like to use simple terms when we're explaining things to people who have never been taught how a nuclear reactor works for the first time. So when I was taught about nuclear fuel, it's like a Pop-Tart. Okay. So how do you build a nuclear reactor with Pop-Tarts? No, not really. It's what you feed the people building it, right? No. It's not that. So is everyone familiar with a Pop-Tart? Pretty familiar? Okay. Does anyone not know what a Pop-Tart is? Okay. A Pop-Tart is a little pastry that has a kind of fruit filling, but pastry completely surrounds it, right? So that's literally what we're dealing with when you're dealing with nuclear fuels. You don't want to put your coolant right on the nuclear fuel because you'll be spreading radioactivity throughout the whole plant. So that is encased in a metal that can touch your coolant. So, Pop-Tart. It's a simple illustration used to teach nuclear power students the construction of fuel rods, because then you take those encased nuclear fuel and then you weld the edges together and you make channels between those plates, and then you can weld those assemblies together, and then you leave a space for the control rod to go down in between all of those assemblies to soak up the excess neutrons. And now you've got a fuel rod with a control rod, and now you've got something. There's a lot more that goes into it, and we could probably talk a little bit about it if you have more questions in the Q&A. And these are pictures from Wikipedia. The one on the left shows a functional diagram of fuel. You've got fuel there, moderator, and the control rod. So these little things are the neutrons, and they're what's required to cause fission. So by removing this rod, more neutrons interact with the moderator, make it back into the fuel, because that's where the fission happens. So the neutrons are shot out of there, but then the moderator helps them to come back in to cause more fission. So with this control rod all the way down, it's absorbing enough neutrons to shut down the reactor. And I added the red box so you can kind of see the kind of Pop-Tart concept going on. It's fully encased. They say fuel rod, so basically I just took a rod and turned it into a fuel plate, but then if you stack all those up together, you create that fuel rod. In the picture on the right, the red thing in the middle is the reactor. These are pumps. These are steam generators. That's a pressurizer. These are your pipes. So red for water coming out of the core, hot leg, cold leg. But this is several hundreds of degrees. Cold leg sounds like it's, cold pool water. No. It's 4 times hotter than a hot tub. But that's our cold leg. This is actually a Chinese reactor plant. Again, I took pictures from Wikipedia because I know I'm pretty safe to do that. So I've never seen a core like this, but it looks similar to this in overall architecture and the arrangement of the different items. So let's step outside of the nuclear reactor for a second and look at the whole power plant. So you have, from the previous picture, you've got the reactor, the coolant pump, steam generator, and the pressurizer, and now they're inside this domed building here. And then you've got the secondary loop, which is where you take your steam and turn your turbines. and your cooling tower. So if you've ever driven by any power plants, coal-fired or nuclear, these are the things that look the most impressive. And I would assume that many people think, when they think nuclear power, especially because I've seen it in movies, people are thinking this thing. But if you look over to the side, this little humble dome structure, that's where the real power is. And there's nothing nuclear over here. So there's two loops. A lot of our reactors are pressurized water reactors, some boiling water reactors, but most of them are pressurized, and all the Navy ones are pressurized. And so the steam generator is actually a heat exchanger. So this water, which doesn't touch the nuclear fuel, but you can't contain every little bit of it, right? So they can have, you can have a little bit of radioactivity in there. We filter that out. But here, we exchange the heat into a secondary water, a second loop, and that's what we turn to steam, and that's what we use to turn our turbines. So out here, we monitor any steam leaks for radioactivity, because there should not be any radioactivity in that steam. So by the time you get out here, this thing's not nuclear at all. So I live near Shippingport, Beaver Valley Power Station, and it has two of those dome-shaped buildings, thus two nuclear reactor plants. You can go on the NRC website, that's all there. And they'll tell you what power levels it's operating at on a daily basis, too. But down the road from that is an old coal plant that's been shut down. And they have 3 cooling towers. And so, yeah, cooling towers are not nuclear. But everyone thinks nuclear when they see the cooling towers. It's pretty wild, right? So really, if you know anything about energy production, a lot of old steam systems used boilers to create steam to drive turbines for generating electricity. And before we go to the next slide, we can summarize everything in the nuclear reactor as hot rock makes water hot. So when you're a nuke and everything is pretty serious and very bureaucratic and a lot of checks, checklists and everything, we make our fun this way. We describe the processes quite simply and take our humor that way. So hot rock makes water hot. But we can go more into how that process actually works if you want in the Q&A. But since we only need a simple drawing to talk about the steam plant, I borrowed this one from Wikipedia so we can see how to push the submarine through the water and keep the lights on. For our purposes, the boiler represents the pressurized water reactor. The steam generator is the heat exchanger in a 2-loop system, which I mentioned, which generates steam in the secondary and not in the primary loop. So that previous picture, you have the primary loop. The pressurizer keeps high pressure on it to keep it from boiling, except in the pressurizer itself. Again, technical details going into the weeds, but if you're interested in this stuff, feel free to ask me about it. So in the secondary plant, we get dry, saturated steam to turn our turbine blades by the process of impingement. When I first learned about dry, saturated steam, it's pretty cool stuff. Go home, look at a pot boiling on the stove and say, that's not dry, saturated steam. The stuff that you see is actually condensation. The steam is the thing you can't see. Teach that to your wife and, get slapped, but we don't want to actually put condensed steam down the turbines. It would sound like a hurricane or a tornado going through, so you actually want dry, saturated steam down there. But once the energy is taken out, then you start to get condensation. So you get a condenser here, and then it's now back into water as it goes to the steam generators. So that's all interesting stuff, and we can go more into that if you want to know. But anyways, again, with our kind of slightly tongue-in-cheek way of saying it, steam makes the spinny thing spin and the sparky thing spark. So any mechanics in here, anyone who worked on mechanical systems, so we've got our propulsion turbine. So the steam goes into the propulsion turbine. We have forward and reverse, which is different from like driving a car. You actually shift. So if you can imagine, you can put a car in forward and reverse at the same time. You can kind of do that on a submarine. And we can talk more about that if you're interested, but there's some emergency procedures where you have to back up because maybe there's a torpedo or something. So while you have your throttles open to go forward, you're like, ooh, all back emergency, ring, ring, ring. And then you start opening the reverse throttles while closing the head throttle. So if you can imagine, you can put your car in forward and reverse at the same time. That's sort of what you're doing on the submarine. But you're quickly closing those as quickly as you can. But they're on a common shaft, and we don't have it here. We just have electrical generating turbines here. But they go on a common shaft, and then they go into gears that are connected to the propulsion, the shaft that turns the propeller of the submarine, the prop. And the old submarines, they had fixed blade propellers, so we can't keep the shaft spinning in the same direction. We actually have to reverse the direction of the shaft itself. So, yeah, it's really interesting. Let's see, where am I? Yep, steam makes spinny things spin and sparky things spark. And so similarly, we have electrical turbine generators. Anyone work in the electrical industry? Yep. So it's really fascinating stuff of how we start applying pressure to the turbine generators and get them up to speed before we actually start to draw electrical power from them. But we have an electric plant. We have a battery on a submarine. That's our backup power if all else fails. We also have a diesel generator. And so everything is connected into our electric plant. And yeah, we have built-in redundancy, so two sides of the electric plant, we keep them separated. We don't want electrical transients going back and forth. And so we need electricity for battery, lights, air conditioning. And you'd think air conditioning's for the people, but it's for the electronics. Just kidding. People can stand near the electronics to cool down, though. When you're in the steam plant, it gets really hot. So as a reactor operator, I had the benefit of being in the, what we call maneuvering. It's a control space for operating the plant. And that space you actually condition, so put in air-conditioned air. Feel bad for the operators that operate outside that space, checking all the pumps and the steam plants and oil systems and everything. They get the hot work. But yeah, we have a lot of things to power: refrigeration units, high pressure air compressors, hydraulics, sonar, radios, fire control. Because you may have to deal with a surface ship. But if you look close, you'll see this is the top of a building in the foreground. And since submarines don't fly, you probably need an explanation from me for how I got this picture. Before we get there, that is the ex-USS Ranger being towed out of the Puget Sound to its final place where it'll be turned into what we colloquially say razor blades, or whatever they're going to do with it. I just happened to be at the Pacific Science Center in Seattle on the day they were towing it, and looking out of the Puget Sound through an old optical submarine periscope that they had set up at the Science Center. So I snapped a picture with my phone through the, thought that was pretty wild. So that's at the Pacific Science Center. And so that's the periscope that I was looking through. That's fire control. Those two boys, the one at the fire control, he's 17 now, and the one looking through the periscope, he's 16 now. So this was a while ago. That's an optical periscope. We actually have digital periscopes now on submarines. And so one of my props is a stopwatch, because you need it when using the periscope. So you can only look in one direction at a time, right? And you must constantly scan around to see around the submarine 360 degrees when at periscope depth. But there are things worth investigating. I saw night fishermen with lights shining on the water and watched them for a bit, but you have to get back to rotating, hence the stopwatch. I have other props that I think I'll talk about shortly. But one last thing. The near future will see a resurgence of nuclear power in the U.S. This is my opinion, and I've talked to some other people, and it looks like it's coming. I was talking to my wife about this because I'm a nerd, and she has to put up with my nerdy stories and talking about things I'm interested in. Before we left Seattle in 2022, we came here so I could finish a master's program in divinity at Trinity Anglican Seminary in Ambridge, Pennsylvania. But I realized that we could possibly stay in the Pittsburgh area because of the nuclear industry. I saw the proposals for small modular reactors by General Electric, GE Hitachi, and Westinghouse. I saw them online and hoped that this was going to be a reality. And I've been on the job boards for Bettis Atomic Power Laboratory, looking at jobs that were available for several years now. I've watched the shift in the types of jobs being listed. Since nuclear power is central to my career, I could read between the lines on some of these job postings. I'm like, oh, they're shutting down the hot cells and such, defueling, decontaminating them and things. So in 2 years, I'll be looking for a job. I'd prefer to work in small modular reactors or microreactors, simulators like I mentioned, test engineering, many more areas. I love nuclear physics and really enjoyed learning about source neutrons, reactivity, heat transfer, metal alloys, radiation detection, and so many other areas. Feel free to ask me about any of that in the Q&A. Anyways, I've already met people who work for Bechtel and Westinghouse, so I know there's plenty of work out there. But if you're interested in my experience, certainly come talk to me, because I'd like to re-enter the field after completing my sabbatical in personal development. So it looks like in the 2030s into the 2040s. So in the 2030s, we'll be working on improving designs and then building the test platforms. And then it looks like in the 2040s, really approving them for commercial production. But that's all from like the NRC web, the Nuclear Regulatory Commission website and stuff like that. So that's all projection. And it's a good thing from my perspective. I don't want to debate what the definition of green energy is. I only want to say that nuclear is one of the sustainable paths forward. And if I were a betting man, I'd bet on it. I'm not against fossil fuels, but we certainly can do a better job with pollution. But I know that if we don't let Chernobyl, 3 Mile Island, and Fukushima make us go a little crazy about nuclear, we can actually learn from those incidents, which we have, and we can spark a nuclear renaissance in the U.S. And I look forward to being part of it. Now let's take a look at some of the props that I brought. If you want to turn the lights on. And if you want to ask any questions, this would be a fine time to ask questions as well. What do you got?
Here, hold on a second. Ooh.
How knowledgeable are you about where the Chinese are with regard to nuclear power?
I'm not very knowledgeable on what foreign powers and their nuclear capabilities are.
Joe? It seems like every reactor has to have cooling towers. How do you accomplish that in a submarine?
That's a great question. So let's see, I can go, well, I'm not going to go back. All right, so we talked about the two-loop system, right? The primary water that touches the reactor, losing. And then there's the secondary, which you use to turn into steams. And you remember I pointed out the condenser? The condenser is a heat exchanger, and so on submarines we use seawater as you could call it a third loop if you want, but we have seawater that goes through on the seawater side of the condenser, and it removes the rest of the heat from the kind of low energy steam to finish turning it back into feed water. So cooling towers, if you notice a lot of nuclear power plants like around here, right on the Ohio River, so there's your source of water if you need it.
Yes, my question is this. If one of these nuclear submarines sink in the deepest part of the Pacific Ocean, What happens to that nuclear core? Does it disintegrate or what?
So I can't tell you with certainty what happens, but water is one of the best things for shielding and for cooling the reactor core. And that's why we use pressurized water reactors. If the submarine goes down, it depends on how it goes down, but the control rods should be fully inserted into the core to absorb the excess neutrons. But that doesn't mean the water will continue to flow through the core. So you could have the fuel elements overheat and cause blistering and other things on the in the metal that encases it. So you could have some release of radioactivity, but there's multiple stages of containment. So even just being released to the primary coolant would still not allow it to get into other parts of that submarine yet. And so it would have to make it through a lot of layers of containment. You'd probably have, my guess would be you'd have core damage, but I don't think you would ever be able to measure it in the ocean. Yeah, I'm thinking about it. Again, there's multiple layers of containment, and I'm just trying to think through. This is a good question. It's like how we do any kind of analysis for accidents and stuff. This is beyond what we would analyze because your question assumes there's no operators now. So there's nothing I can do to save the core at that point. And so this would be beyond what we would normally analyze. But even with core damage, you still need water flowing through to pick up any excess radioactivity to spread it through the ocean. The ocean's very, very large. And like the idea that a submarine would go down, and I don't know if there's a concern behind the question, but the idea that if a submarine went down, imploded, the core had damage, released radioactivity, and we'd be able to measure it here is very, very low on the probability, because that's how big the ocean is, and there's a lot of natural radioactivity already in the ocean, so we might not even be able to measure it. Now, we have very, very fine measuring instrumentation, so I'd bet, being on the West Coast, well, I was in the Pacific Fleet, but being on the West Coast long enough, if someone would say, oh, there it is, I see a little signature, but it'd be nothing even close enough to be anything to fear for anyone who lives in Hawaii or in California. It wouldn't even be close to that. But exactly what would happen, damage is high probable, but beyond that, spread of reactivity is essentially negligible.
What does it mean to scramble the reactor?
Scram. Scram is what we do when we insert all the rods in to shut down the reactor core. So when we think about whether a reactor is critical, we talk about reactivity. And so we have control rods that have a large amount of negative reactivity. So we want to shut that core down really fast. I have a switch that I can turn that will release the control rods, and they'll go to the bottom of the core with, I think, milliseconds, I think.
Okay, I got another question. I was an engineering officer on a submarine supply ship. I'm in Holy Lock. So we served the Abraham Lincoln, George Washington, and Thomas Jefferson. You talked about the turbine plant. On the back end of the low pressure unit, that's the unit for the reversal of the turbine. On the nuclear reactor, do you know anything about the blading? Or is it reaction or impulse blading?
You're taking me back. So impulse, we've got the curved blades. And reaction, we got the Nozzle?
The power end is the reaction blade, but the on the smaller generators you have the impulse because you really.
Yeah, I'm trying to think, because I remember we had to draw these turbines, and we had to know which, fixed blades, curved blades, but we used impingement blades. Yeah.
That's good enough. Thank you.
Yeah. You're taking me back. We had nozzles to increase the speed and impingement blades. Yeah.
I have two questions. You might not be able to answer them because they might be classified. Physically, showing us your hands or giving us square feet or whatever, how much not radiation, but isotopes in size-wise do they put on the ship?
So you're talking about nuclear fuel?
Yes, nuclear fuel.
I don't remember the number, which I think would be confidential. But the different reactors are different sizes. So submarine reactors are much smaller than like the aircraft reactors. I haven't seen the actual core itself because not only do we have all the rods going through it, and then all the there's shielding because neutron embrittlement, neutrons will destroy everything. And so we've got shields to absorb the excess neutrons, making it out of the core. Then you have the pressure vessel because the whole thing is pressurized to a very high level. So by the time I see the outside of this thing, like I'm looking at the pressure vessel and it's like from floor to ceiling and pretty wide. And then the different, when I mentioned the S5W, S9G, these different cores are going to be different sizes. So the Polaris submarines would have the smaller cores than like the newer submarines. So, but what I was told by someone that the core itself, where the fuel is probably about the size of like a large trash can in terms of like the amount of fuel. But like I don't think I could get more specific without saying a number, and then, which I don't remember anyway, so it's all good.
Second question is, you indicated that the submarine has a secondary cooling and they use the seawater. Well, there's going to be a certain amount of ambient heat being generated out in the ocean. And with satellites now, they can track the difference in heat. What does the Navy do, or what do we do to eliminate being tracked by these other countries?
I don't know how much we can do. I've had people tell me different things about how submarines can be tracked, and I'd like to think, especially when I was on one, that I was more invisible than I probably was because of things like you're describing. The ocean's really big. It's very large. So, and the ocean's not as homogeneous as you think. There's different salinity in different parts of the ocean, different temperature layers, and columns even. And so, like, without going too much into that, because that affects how submarines operate. But like, I don't have a direct answer to your question. Like, I don't know what we do specifically for that, except clandestine operations. You go deep and you stop moving if you can, right? That's, if you're trying to really be clandestine, you want to go as deep as you can and move as little as you can. That's not 100%, like, there would be caveats to that for different, underwater geographical, but also like the conditions of the water itself would change that advice. But you could see, hiding is what you need to do. But everything in the ocean makes sound. Like, you talk to any sonar techs and they're hearing all these bubbles in the water and like, oh, biologics. So whales, schools of fish, and things like that. I didn't get to go to a foreign port. I got Guam. Got to see the Philippines through a periscope. And then we were going to go to Japan. I was like, yes, this is awesome. And then, oh, we hear an enemy submarine in the water. Let's go chase it down. So I didn't get to go to the really cool port in Japan. But, then we eventually lost it. So, like, you can have indications of things, but you won't always be able to pinpoint exactly where a thing is. With what you're talking about specifically with temperature, if you're using satellites, I don't know what the answer to that is.
Pressures on the system. I'm just curious because I'm familiar with surface ships. We always refer to the power plant being 600-pound steam plant or 1,200-pound steam plant. So what's the submarine pressure, system pressure?
It's going to be the first one
First one, 600?
on the steam side.
Thank you. That's all I have.
Okay, it's 11 o'clock. Mike, thank you for your presentation.